this video, I want to look at an example problem which makes use of our equations of motion and looks at them in a couple of different ways, so we can kind of relate this to what I've been talking about with in terms of general planar motion and the equations of motion as they apply there. So in this problem we have a spool that is supported by tension on a cable or a rope which is connected to the spool at point A, and that's fixed to the ceiling or whatever this happens to be. And then it is raised and lowered by a cable attached to the smaller gear or pulley, and 100 Newton load is used to raise, let's say raise in this case, to raise the spool up. We're given that the mass of the spool is 8 kilograms, and we want, and the radius of gyration is 0.35 meters, and we want to find the angular acceleration of the spool as it's being raised up with this 100 Newton force. So a couple of things that we'll first want to do is make some conversions, calculate some of our base quantities. For that, I would first take my mass and convert it into a weight via gravity. Making that multiplication, I get 78.48, so about 78.5 newtons. Radius of gyration is a kind of another way to express the moment of inertia. Basically, it's making the simplification that if you took this entire mass of this spool as it's distributed over this circular cross section and concentrated it at a single point at some distance from your axis of rotation, what would that distance between that point and the axis of rotation need to be to have the same moment of inertia? So it's just another way to express that. It has units of length, as you can see here. The radius of gyration is 0.35 meters, and we can make use of that to calculate the moment of inertia about the center of gravity, G, using the equation m kg squared. As a result, we get 0.98 kilogram meter squared for our moment of inertia. Okay, so to start analyzing this problem, we'll set it up in the way that we would set up most problems that we're trying to solve, and that is with a free body diagram, kinetic diagram pair. So I'm going to kind of redraw my rigid body in free body diagram and in kinetic diagram positions. So if I look at my free body diagram and kind of think about what kind of loads I have applied, I have to provide some load, which I'm going to call a tension, give it a variable name T, for the load that's being carried by the rope attaching it to the ceiling. We have our applied load of 100 newtons, and then we have the weight of this whole thing, which acts at its center of gravity, pulling down, and we calculated that to be 78.48 newtons. So that's our free body diagram. I think we've accounted for all applied and reaction loads as well as the weight. Now we're going to set that equal to our kinetic diagram. Possible motions for this: as it moves up, we can expect the whole spool itself to move in an upward direction. So that's realized on our kinetic diagram as a mass times an acceleration of the center of gravity G. Also, as this is happening, we would expect the spool to rotate. So I'm pulling up here with this 100 Newton load. It's fixed at A over here, so it's moving up and rotating, and therefore I can apply that to my kinetic diagram as IG alpha. All right, so we've got a free body diagram, kinetic diagram pair, and now I want to go about solving for the angular acceleration. So normally what I would do is sum the forces. I'm going to skip summing the forces in the x because I don't have anything in the x direction. So I'm going to sum my forces in my y or vertical direction. And I'm going to set that equal to my mass times my acceleration, which again we have over here. Being consistent with my drawings then, I would write this out that I have T plus the 100 Newton force minus 78.48, taking into account all of my forces, equal to MAG. All right, so I think I've got everything accounted for there. Next, I'm going to do a moment balance about my center of gravity, which looks like that, and start plugging in what I have. So I would look at my forces as they're applied. Again, G is located here at the center and A is located over here where T is attached. So what forces contribute to my moment about the center of gravity? Well, I need to look for anything that has a moment arm. My weight here has a vector that passes through the center of gravity, and therefore it has no moment arm, which means it doesn't contribute to the net moment and doesn't show up in that equation. However, my other two forces, the 100 newtons and the tension, do contribute. So if I go ahead and write these in, then I'm going to have a contribution from the 100 Newton force at a distance of 0.2, which was given as the radius of that inner circle. And I'm going to put a negative sign out front because generally, as a sign convention, any force or load that would cause a clockwise rotation of my rigid body contributes negatively to the moment. So we would usually say counterclockwise is our positive sign convention, but again, that's just a convention. We don't necessarily have to stick to it, but I like to use that one. To this, I'm going to add a contribution from the tension, which is out at a distance of 0.5, which is again given as the radius of the larger circle, 0.5 meters. All of this I'm going to set equal to my right-hand side, which is Ig alpha on my kinetic diagram. So looking at this, I can see that I know my mass, I know my mass moment of inertia. Maybe I should actually just substitute those in to simplify. 8 here and 0.98. Noting to myself that I've also forgotten a negative sign out front because the way I drew this arrow is a clockwise rotation. I could have drawn it the other way, but I drew it in a clockwise direction, and therefore I need to represent it here negative. Again, that's a convention. As long as my convention is consistent, then everything will come out. If the arrows prove to be in the wrong directions, then my answers will come out negative, and it tells me that through my solution. All right, so looking at this, so far I have the linear acceleration of g, the angular acceleration, and the tension t. So I have 3 unknowns and only 2 equations. So that's potentially problematic, right? However, we do know that there is a relationship between these 2 accelerations because the acceleration of g, which is here, is related to alpha because my whole rigid body is rotating basically about point A at this instant that this motion is occurring. A is fixed. It's attached to the rope that's attached to the ceiling and can't move. So I can relate these two by saying that AG is r theta, where r is the distance between A and G, which was 0.5. So that gives me an expression, or a third equation, that coincides with my three unknowns. All right, so from this, I can go ahead and substitute this into the top equation. Now I have two equations and two unknowns. And if I solve them all, I get alpha equals 10.3 radians per second squared. Ag equals 5.16 meters per second squared. And the tension in the rope is 19.8 newtons. So I didn't necessarily need to solve for Ag and T, except that they're part of the same system of equations, and therefore I needed them to be able to solve for alpha. I'm going to call this solution 1 because I want to look at a couple of different ways to solve this problem. So for solution 2, I want to take into account that I don't necessarily need to sum my moments around the center of gravity. I can pick any point to sum around. So as an example in this problem, it might be convenient to sum the moments around point A because that eliminates what's going on with t as a variable. It eliminates it from the equation, and it maybe simplifies my expression a little bit. So let's see what happens if I do that. Now, one thing we have to be aware of here is I only know the moment of inertia about g, so I'm going to write that in, Ig alpha, but now because I'm not rotating or taking the moment around g, I need to add in the fact that my body, my rigid body, is moving or accelerating about this point A at the same time. And I can take that into account by multiplying the mass and the linear acceleration by the distance between those two. Now if I do this, I end up with an equation that looks like this. First, summing my moments about A, for which I have two contributions, one from the 100 Newton force and one from the weight. So I get minus 100 at a distance of 0.7 because I have both radiuses added together, plus 78.48 at a distance of 0.5. Set this equal to the right-hand side, which is 0.98 alpha, and clockwise contribution as well, so minus sign from MAG, which is 8 times AG times 0.5. And I have two variables here, but once again I can note that AG equals 0.5 alpha. And now substituting that into the first equation, I have one equation with one unknown, and I can use that to go ahead and solve for alpha, in which case I once again find 10.3 as my solution. All right, I want to look at this just one more way, so we'll do a third solution. So I mentioned that point A is rigidly fixed, and at this instant in time, as my spool is moving, it's rotating and translating. However, point A is not moving, and therefore, by definition, point A has to be my instantaneous center, which I've talked about before. So as an instantaneous center, it allows me to look at this problem in a slightly different way, which of course will come out to be the same with the same solution. But if I treat A as an instantaneous center, meaning that my rigid body is rotating about this point at this instant in time, I can do my summation of moments about the instantaneous center, which is of course same as point A as we did last time, take the moment of inertia about the instantaneous center times alpha. Now, if I do this, I once again have the same left-hand side that I saw up here because I still have the same contributions to that moment. My right-hand side now, I need to know the mass or the moment of inertia about the instantaneous center, or about point A. Well, to do that, I can write it in terms of the parallel axis theorem, which, if you'll recall, is basically the mass times the distance squared. So if I do that, I get 0.98, which was I of g, plus mass times distance squared, 0.5 squared. So this is the distance between g and a. Now you'll note that this 0.5 squared ends up being the same as what I have up here, right? I have 0.5, and this 0.5 times alpha comes in and makes it a squared, and it ends up being exactly the same, right? So it's not that it's a different formulation. It's the same equation, same formulation. It's just a different way to think about it. And of course, then, since this equation is exactly the same, as expected, alpha comes out to be 10.3 radians per second again. Second squared, excuse me. So 3 slightly different ways to look at the same problem. Of course, the answers come out to be the same, but it kind of helps us to have different ways to look at it, different ways to think about it, because sometimes some situations one version is easier than another, or maybe it helps us with things that we know or don't know in a given problem. All right, thanks.